Hello, everyone. My topic today is about a Spark HBase Connector, which is a library to support Spark accessing HBase tables as external data source. With it, user can operate HBase by Spark SQL. So I'm a software engineer at Hortonworks and contribute to Apache Spark, HBase, and Barry, and Hadoop. Today, I'm going to talk about the motivation of this connector and why it's good for use and what is architecture and implementation and how to use it. So before, why we need to develop a new Spark HBase connector? Actually, before starting to develop this connector, we were trying to find if there were existing connectors we could use directly. There were some open source connectors available either as Spark packages as independent projects or in Apache HBase. So we needed to evaluate the solutions. First, we needed to decide at which level this connector should be, at RDD level or at data frame level. The HBase connector in HBase chunk has very rich support at RDD level, but the data frame support was not rich at that time. On the other hand, the Spark has moved to data frame dataset APIs with built-in query plan optimization. So the end user prefer to use data frame dataset APIs. So we decide to make this connector at data frame level. There were also some connectors available at the data frame level, but their design are very complicated. For example, they use very advanced custom optimization by embedding their query plane optimization inside the standard Spark Catalyst engine and ship their RDD into HBase and perform very complicated tasks inside HBase coprocessor. Those approaches are able to achieve high performance, but as we know, Spark evolves very quickly, so it's very hard for them to maintain those connectors due to the complexity. So we decide to develop a new Spark HBase connector to overcome those potential bottlenecks and weaknesses. In the following talk, I will briefly mention this Spark HBase connector as S3C. S3C leverages Spark Catalyst engine for query plan optimization and use HBase as fast access key value store and implements Spark standard data source API. Its design makes the maintenance very easy, and while achieving a good trade-off between the performance and the simplicity. Since no matter how spec changes, the data source API keeps stable. Full-fledged data frame support. HBase data frame is a standard Spark data frame, so user can query HBase data by Spark SQL. If you are familiar with data frame API like join, group by, select something, you can also use integrated language. We didn't do any optimization with HBase coprocessor, but we do care about the performance. We didn't use standard HBase RDD. Instead, we construct the RDD from scratch. With the customized RDD, all the credential taglets can be applied and fully implemented, such as partition pruning and data locality, column pruning, and predicate pushdown. How to achieve all of them, I will talk about them later. Using Spark and handled filter API is a effective optimization. It tells Spark about filters which hadn't implemented in S3C, as opposed to returning other filters. Without implementing it, Spark will reapply those filters again once the data returned from HBase. Sometimes replying all the filters inside HBase, inside Spark again, doesn't change any data, but it could be very expensive if the filters are very complicated. S3C cache Spark HBase connections. Actually, at the very beginning, S3C did not cache any connection objects. It means the call to creation was done each time when tasks needed to visit HBase table and region. In Apache HBase, there is no connect pooling under the hood, which has been removed from the master code. The connection creation is a very expensive operation. So, and its optimization are thread safe. So it's very useful for S3C to make the connection cached. With this feature, S3C can decrease the number of connection creation and greatly improve the performance. In order to save the data into HBase, we need to convert data types into HBase byte array. So in S3C, it supports several data coders. User can make choice based on their needs. The primitive type coder is a custom serialization using very simple native encoding mechanism. It uses HBase encoding and decoding and do extra words to resolve the order inconsistency between Java primitive type and HBase byte array. S3C can use it to support Java primitive types. S3C also support arrows format, since it's a very uncommon practice to persist the structured data into HBase as a byte array. Users can persist arrow records to HBase directly. S3C fully support all arrow schemas. Internally, arrow schemas are converted into Spark catalyst data types automatically. So for the exact usage, you can refer to the S3C GitHub document. There are detailed introduction. The user also can also config S3C to use Felix encoding and decoding. Given the popularity of Felix data in HBase, it's very nature to support Felix data as input to HBase in addition to arrow data. Also, defaulting to a native simple primitive type data coder seems susceptible to future changes. With, for example, with S3C going forward, the backward compatibility needs to be properly handled. And also, Felix encoding and decoding support complete key very well. So it's good for S3C to use a more standard and well-tested data format like Felix encoding and decoding. The users can also implement their data encoding mechanism and decoding mechanism. S3C support plugin data coder. S3C can run on the top of existing HBase tables as long as they follow Java primitive types, arrow records, Felix data types, or the data types the plugin data coder support. Support complete key. As the example here, S3C support complete key very well. Here, the cat definition, it uses Felix as the table coder. And the row key has 2 dimensions, key 1 and key 2. But one thing we need to pay attention to is we only do optimization on the first dimension of the complete key. It's very challenging to do the optimization on all the dimensions of the composite key is our feature work. So let's look at the architecture and implementations. As the diagram shows here, we assume Spark and HBase are deployed in the same cluster. It means Spark run along with HBase. The upper part is in Spark side, and the lower part is in HBase side. And Spark executor are collocated with HBase region server. In this deployment, we can get the benefit of data locality. Of course, you can deploy a Spark and HBase in different clusters, but in that deployment, you will not get the best performance. So when a query comes in, the Spark driver will compile it. Then we can get the filters and required columns from Spark Catalyst engine. And based on the region's metadata like the start point and end point, we can construct the RDD partitions. As we know, in Spark, one partition corresponds to one task. And in SRC, we make one partition corresponds to one region. And the driver aggregates, scans, and gets based on region's metadata and generates tasks per region. If a region doesn't has the required data, that region server will not be assigned any task. So note that the driver doesn't is not involved in any real job execution except scheduling the task that avoid it being the bottleneck. The tasks are assigned to preferred executor. The executor performs the task on local region server. It means the tasks are performed in parallel in executor to get better data locality and concurrency. At a high level, this connector treats scan and buckle gets in similar way. Both actions are performed in the executor in parallel. One task may consist of multiple scans and buckle gets. A required data inside a task is retrieved from only one region server. That region server, of course, is the locality preference to the task. So let's go to the implementation first. The partition pruning. Partition pruning, it means Spark tasks are only performed in region servers holding the requested data. We can get maybe there were thousands of region servers in the HBase cluster, but we only send the task to the region servers holding the request data. For other region servers, if they don't have any requested data, we don't do anything on them. So from the query, we can split the filters into multiple scan ranges. And in the HBase side, we can get the stop. We can know the region's start point and end point. So then we can do intersections between the scan ranges and the region's start point and end point. Then we can know if the region has the data or not. If the region has data, we can know which scan range falling to that region. Then we can do this for all the regions in the HBase cluster. Then we can know which region has data and which region hasn't data. Based on those information, we can construct RDD tasks and send those tasks to the region server holding the request data. And for one region server, there may be multiple scan ranges. And this is how we implement partition pruning. Data locality. Data locality means we move the computation to the data. In S3C, it means we move RDD tasks to the region server. How we do this? So we have already know the region, which region holding the data and which scan range are in that regions. So the left thing is straightforward because we can get the host of the region server from the HBase metadata. Then the only thing we need to do is to set the preferred location of that task to be the host of the region server. This is API and Spark data frame provide to us. Column pruning and predicate pushdown. So we can get filters and required columns from HBase from Spark Catalyst engine. So there may be thousands of So there may be a lot of columns in a HBase table, but we only retrieve the required columns from the region server. That can reduce the network overhead and the avoid the redundant computing in HBase in Spark Catalyst engine. So predicate down, we use standard HBase filters to do the predicate pushdown. We construct filters into scans and gets and ship them to HBase, and HBase will do the filtering for us. Scan and buckle gets. It means we send multiple scans and buckle gets to region server. Internally, we convert the while clauses into scans and gets. So how to use it? There are a detailed introduction how to use S3C in S3 GitHub repo. The S3C is an open source project, so you can feel free to download it and use it. You can submit your questions, and we will feedback it as soon as possible. You can also propose your PR there. There are examples in S3C GitHub repo, so you can refer them to understand how to use S3C and how to write your own applications. So one thing I want to mention is for Spark, it only supports the cases which access one single HBase class, secure cluster. If your application want to access multiple secure HBase cluster, you should use S3C Credential Manager. So I will skip the demo here. And the following slides is related to how to use S3C. All the information are already in the document in S3 GitHub. If you are interested, you can refer them there. So yeah, that's it. Yeah. I think there's not enough time for the question.
Let's do one question.
Okay.
You choose. You choose.
Oh, we won. Okay.
Okay.
So your connection between Spark and HBase, is that a deep connection, or do you go through the HBase interfaces, the client interfaces?
Excuse me, could you?
Does the connector use the HBase client interfaces? It does. Okay. And you use the Apache license for the open? Sorry, what license do you use? Okay, cool. Mine was really fast.
We need to move on to the next one. Sorry.
Yeah. If you have questions, please feel free to email us. Yeah.
Thank you.